All right, thanks for coming to my talk. I'm wearing the other shirt from Text by the Bay from last year, just to show respect. So the usual disclaimer, these are not Microsoft opinions on label quality, they're just my opinions. It's joint work with a bunch of current and former Microsoft colleagues. A quick outline. I'm going to be talking about the problem of acquiring good labels in the context of big data. And then I'm going to be talking about three main things. The first one is wet word programming, or how to program people, how to debug and test human computation tasks, algorithms for quality control, and then conclusions. So I'm assuming you have a bit of a background on how to run human computation tasks. And by the way, there's a lot of technical content, so I try to add a footnote as a paper or a book, so you can go and read those things in detail. I try to abstract the more important concepts for the presentation to minimize math and algorithm work. Okay, so I'm assuming you have an idea of what human computation is, which is basically how to use humans or people for things that machines are not very good at. And this idea has been studied in particular by Louis Bonan from CMU, who was doing CAPTCHA, and also this notion of games with a purpose. So you can play a game, but under the covers what you're doing is just basically acquiring data for a bunch of other purposes. You're probably familiar with platforms like Mechanical Turk or Crowdflower, where you can just create a hit, which is a human intelligence task. You pay a few cents, and people will do stuff for you, and then you collect the data, and without that data, you just train your models. So in our case, for this presentation, every time I talk about human, it's going to be about a worker. You're producing some work, or you're a rater, or you're an annotator, or you're a judge. But the idea is humans are going to be doing stuff for us. A bit of a context. It's about supervised or semi-supervised learning. So this is not unsupervised learning, supervised or semi-supervised. We're going to ask experts or users to do a task. The task is usually a little bit different from the real work, because we're assuming you're going to do this, so it's a little bit artificial. And there are two main important things from industry here. One is scalability. We're not interested in just getting 100 labels or 1,000 labels for a paper. This is massive scale, thousands of millions of labels. And the second is continuity. It's not a one-off job. You do this every day, or every week, or every month. Okay, so the crux of the problem, why we need labels. Labels are super important for information retrieval. You need collections to start bootstrapping a ranker so you can search stuff on the web. For natural language processing, you need to tag all these things to get sentiment, to get name entity extraction, etc. For machine learning, obviously. Active learning, artificial intelligence, in particular if you're trying to build models that are a hybrid of humans and machines. And a sample of common tasks, at least today, for gathering labels are content moderation, the usual stuff. There's adult content. You have to build a classifier that can detect this. Information extraction. Please extract the name of the person from a page. Search relevance. Are the search results relevant? Entity resolution. Is IBM the same as International Business Machine? And a bunch of other text processing. There's a great book, Crowdsourced Data Management, that was published recently, which they did Aditya did a very good job at just running this survey, just to get perspective from industry on how these things are going on. So what is a label? So a label basically means that we want to get or tag a particular object with some sort of scale. So if I'm looking, for example, for a page, and the query is Text by the Bay, and I get this page about Text by the Bay, is the page relevant? And probably I have three answers. It is relevant, it's very relevant, somewhat relevant, and not relevant. And we'll consider that maybe a label. Or you usually have this typical spam email message, and you want to know if the message is spam or not. Again, it's a classification problem, and the labels are yes or no. However, in the area of big data and machine learning, we have to be very, very careful with labels, right? Because labels are used to compute features, that we use the features to build a predictive model, and then we do optimization. But label and experimentation, unfortunately, are perceived as extremely boring side of the house because everybody wants to play with support vector machines, neural networks, you name it, word2vec. Everything is super cool, but nobody wants to actually get the data. So there's a tendency in the real world to rush the labeling process. And I'm going to argue against that rushing. I'm going to tell you why this is important. So I took this picture from Twitter, and this is a typical, nothing against the Twitter account, but this is a typical example that you'll find today in machine learning. Everybody's doing the engineering, modeling, visualization, and how to do that. But if you can see from the picture, the gate data, ETL, is gray. Nobody wants to work on that. The talk is about how to work on that. And in case you say, well, but who cares? We don't need humans. Can do deep learning and all those things. You will always need a human. You need the humans to do the training. You need the humans to do the experimentation. You need the humans to do the evaluation. It's a great article, by the way, a couple of years ago on Wire on how Facebook is using a third-party company to get all this adult content. You probably heard from Ricardo's talk, all the bias are on the web, and you probably heard the news from Facebook on the bias on the news, and you can read the rating guides for trending topics, et cetera, et cetera. Why is this important? Because there's a life cycle of the label. And I'm going to use information retrieval example here. So in information retrieval, usually you need to ask people to annotate a collection of relevant, non-relevant content, and based on that, you build a ranker and so forth. So how this works? We start with the following. We have a data set, so we have a collection of documents, and I'm a judge, and I have characteristics. So the documents already have some characteristics. Maybe the documents are politics or sport. As a judge, I also have characteristics. Maybe I do like sport, maybe I don't like politics. My task is to do judgments. I'm going to do judging on a document and a query, and I'm going to produce a judgment. Because I'm a human and I can have an error, another person will do the same. We're going to do an aggregation of those judgments, and we're going to produce a label. Okay, that part is basically using a crowd to label a data set. The second part is we're going to use the label to produce some learning model. We're going to learn the model so we can predict the rest of the labels. And with the rest of the labels, you can annotate the rest of the collection. Also, the labels are going to be used later to evaluate the performance of my system. So what I'm trying to say in the picture here is like they're everywhere. We got garbage in, garbage out is the same problem. If we don't get the correct labels early on, then there's a lot of implications down the pipeline. So label quality, okay. What do we mean by quality? Meets internal customer needs, and it's free from deficiencies. That's our definition. In our case, we want a process where we want rush labeling. We're not going to outsource. You own it end to end. You can crowdsource or you can outsource the acquisition by humans, but you own it, the entire process. It's large scales and it's continuous. And there's another dimension to even make things more complicated. There's a spectrum of labeling tasks. Okay, so we can start with something very, very simple, which is what we call an objective question that has a correct answer. Then an aggregation approach will be to make sure that reliable judges assign an appropriate label for an item, and then the evaluation technique is usually done against a ground truth or a goal set. That's great. We complicate things a little bit more because you're going to have other cases where the task has the best answer, not a unique as before. It's the best answer. It's partially objective. And then we're going to use interrelated agreements to actually measure and determine which is the label for the item. And then we evaluate the technique, basically evaluating the workers by comparing the individual results with the consensus of the rest of the crowd. And there are other cases where this is very, very subjective. So you have to use something that we call repeated polling to determine the probability of the label of the item for an item. And then what you want is to evaluate the workers by computing the consistency of results between groups. So those are the three types of labeling tasks you're always going to encounter. And we're going to use a programming approach for solving this problem. So programming is hard, and there's a lot of very good books, in particular this book by Brian Kernighan and Rob Pike on the practice of programming. I'm going to take a similar approach for writing code that is executed by machines and people. This is the programming view for humans and machines. Okay, I call that wet programming. And there are two important things here. Is, as Don Knuth said, machines have no common sense. They do exactly as they are told, no more and no less. However, we are humans, and we do a lot of errors. So how can we deal with these two things? So if you compare humans and machines, humans executing code, we're not that great. So the instruction set for humans is somewhat unknown. We take our time, so there's latency. We need a cost or an incentive for doing something. We obviously produce errors. Task difficulty is an issue with humans. And there's human factors. I maybe get bored, I'm distracted, I'm lazy, etc. So how do we start? The first one is asking questions. The same way you instruct, you write code. This is part art and part science. Instructions are key. Workers may not be experts, so you cannot assume that they have some understanding in terms of the terminology. Maybe they don't understand relevance. Maybe they don't understand what you mean by label. So they don't understand that. You always have to show examples. And if you can, hire a tech writer or someone who has an English major actually do this for you, and then the engineer will write the specification, by the actual tech writer will write the HIT for you. In terms of the HIT design, the experiments should be self-contained, always in the same place. Keep it short, simple, to the point, clear with the task, engage with the worker. All your tricks and things that you learn from user interface design, document presentation and design, super crucial. You need to grab attention, so have good content, and always look for feedback. If you are doing multilingual tasks, do it in English first, and then you scale to other languages. Other design principles, very quickly, alignment, legibility, reading level. This is very, very important. People are going to read this, so how difficult it is to read, to parse text. There are multicultural, multilingual issues, as I said before. Remember, color blindness, the cognitive load. There are certain things that takes forever to actually understand, and exposure effect, which means that don't ask them to do always the same thing, because as we do the same stuff over and over again, we tend to like it. How we measure this? Once humans are performing the task, as I said before, we have to use redundancy. So usually we have to ask one or more people to provide the answers for us. So then we can measure what we call agreement, reliability, and validity. The first one is to measure the inter-agreement level between the workers. So you can do between the judges or the workers, or between the workers or judges and the goal set. Statistics for this, usually Cohen's kappa for 2 raters, Fleiss if you're using n number of raters, Krippendorf for any number of raters, and in case you have missing values, you can use this. Fleiss and Cohen's doesn't work with missing values. And also you might need to use an internal consistency stat. There's one very popular called KR20, Kuder-Richardson as well. I'm not suggesting that you have to use all of them, but the point here is use one that fits your domain and needs. You have to measure how the workers are doing against your data set. You have to measure with something. This is an example of how to measure. And by the way, do not use percentage agreement. Okay, never use that. Always Fleiss kappa or Krippendorf, KR20. Other practical tips, sign as a worker and do some work. You have to eat your own dog food. Try to address any feedback as soon as you can. Poor guidelines, payments, passing grades, etc. Everything actually does count. Now, there's a human side here, and the human side is, as a worker and myself, if I have to do some human computation, I do hate when the instructions are not clear, and this is in a lot of cases. People will say, oh, I know how to do my hits very well. Incorrect. They have no clue. And this is always the case. People don't know how to write good hits. Sometimes you're not just a spammer, but you actually don't get what the requester is asking you to do. Or maybe the task is boring. And in terms of incentives, you always want a good payment, but sometimes there's something else. Maybe you're learning a new trick, the content is good, You like to look at images, and that's what I'm doing, this image tagging for you. As a requester, your problem is attrition. You always want to have a good crowd that does the label for you. So you always want to maintain the same task force. And it's a delicate act because you want to produce the right results, but at the same time, you want to have good content that is appealing to workers. And obviously, you want honest answers for the task. You don't want fake answers. And you want qualified workers, but sometimes you don't have them. And managing crowds is very, very difficult, and it's a daily job. Okay, it's much harder to manage a data center. There are a number of design patterns. I just outlined some of them. Probably the most interesting is called the Find, Fix, Verify. That's been designed by Michael Bernstein, who is now at Stanford. And the idea is you ask the crowd to do something. So find this, fix that thing, and then you have another person who's going to verify the fix. It's kind of a workflow and works very, very well. Now, we can always go further and say, this is great, but again, from the programming perspective, let's kind of think in terms of program structure and design hits that humans can do very well, but in terms of data pipelines and workflow, instead of having one single hit for everything and then go to the machine learning model, just do little pieces. At the end, you get the label, but all of them are like little things that you do as you go to get your final label. And this involves combining humans and machines. This is a great example, a project called Cascade for taxonomy creation using crowdsourcing. And the beauty of this project is basically they provide and design 3 main hit primitives. So the same way as you have primitives in a programming language, you have 3 main tasks: to generate, select the best, and to categorize. And they all work in some sort of a workflow, all of them on the hits. And then at the end, they have this algorithm called global structured inferencing that is going to get all this data gathered by humans to produce a taxonomy. And the taxonomy that is being produced is very good compared to LDA in terms of quality and price. So you can get more details from the paper. Here's a project that we did at Microsoft a few years ago on near duplicate detection. So near duplicate detection is one of the most important problems on the web because you want to detect if 2 web pages are not only exact duplicates, but if they are near dupes. There was a very good algorithm, and we wanted to know how can we perform the evaluation on this near dupe algo. So we did the following. We used 2 platforms to generate labels. One was UHRS, which is an internal Microsoft platform, and then Mechanical Turk. And we used a 2-phase approach. First, we thought, okay, come on, this is so easy. I just give you 2 documents, and you have to tell me if they're similar or not. It turned out to be a very difficult task because people don't agree what a news article is and what do you mean by near dupes. So what we did is we did two phases. The first one is we do kind of in a cheap way in Mechanical Turk. We go through all these documents and ask the judges, is this document, do you think the document is news or not? Yes, no, that's it. And from there, we use a separate platform, UHRS, which more qualified workers to actually assess if the near duplicates, the 2 news documents were near duplicates or not. This allows us to do the following: separate workforce. So one workforce, we pay less, mTurk, because which is one binary, yes, no, news article. A more expensive workforce in UHRS to actually do the near duplicate evaluation. And this allows you to parallelize. So at the same time, you're just getting all your news labels. If you got candidates, you can already start evaluating the near duplicate detection. And all the details on the paper. By the way, the data is available to download, and also the labels and all the hit templates, so you can replicate all the study. Okay, this is just for writing instructions. This is going to get a little bit more complicated, and is how to test and debug. I mentioned, and I was quoting Kernighan and Pike on programming, and there's a great book by Fred Brooks Jr. on the mystical math month. And you have to always throw a prototype. And unfortunately, in human computation, we don't do that. Sorry. So what's the problem? In testing, we always attempt to break a program, and in debugging, we know the program is broken, and we just need to find out why it's broken. Now, if we compare machine computation versus human computation, at the design level, when you're using machines, you know you're going to throw away the prototype. You do systematic testing, and if something is wrong, it's your fault. Okay, you don't say it's GCC, it's the library, it's my PC or Mac or whatever. It's your fault. Human computation, at design level, we are reluctant to throw away the prototype because, hey, we just paid $20 in MTurk, and why we have to throw this away? The testing is ad hoc. Yeah, we cannot test. Sometimes we test. Sometimes we don't test. And debugging is the workers' problem. There are spammers. They don't want to work. They are lazy people. Well, the news is it's your problem. This is the same as debugging code. You have to do it systematic. You're going to throw away a lot of the hits. And for debugging purposes, first is your problem. And then we'll see if it's the worker's problem. But before doing that, you have to have a development process. And the same way you're going to write code using Agile or Waterfall, or whatever is your metaphor, you have to use some sort of development process. The development process that I'm just suggesting here is just a suggestion. You start with a prototype, which is a very small data set for your own internal team. You do the testing and debugging. You do all these measurements. You do this inter-reader agreement between yourself even and your two other colleagues and coworkers. If everything works fine, then you go what we call an early stage production, which is still a small data set, always small data set, 100, 1K items, crowd-based, mainly for calibration. Do the workers can do the same as you? Can you measure all these agreements? Yes, you're throwing away $100. What's the big deal? Sorry. And after that, you're going to go in continuous production, which is everything works fine, you tested everything, and then you actually go in large scale. You're going to partition the data. It's going to go crowd-based, fully crowd-based, and then you're going to reinforce quality control. So how you test a hit? You follow the same methodology as code. You have to test for validity and plausibility. If you had a problem with the hit, you don't patch it. Okay, you rewrite it from scratch. You're going to version all the templates and all the metadata because maybe this hit was for 3 people, maybe for 5 people, maybe you pay $1, maybe you pay 50 cents, all those things. However, things are going to get very complicated because debugging human computation's task is usually very, very difficult. Why? Because you have multiple contingent factors. Excuse me for the water. We have 3 things. So the workers, maybe they're spammers. Maybe your data sucks. Nobody can actually do any labeling. And, or maybe the task is actually very difficult to perform any work on it. So you have these 3 things in parallel. And we came up with this framework that we're going to iron out each of these elements first. We're going to play with the data. Then we're going to play with the worker. And then we're going to play with the task. So it's kind of a flight checklist to make sure that the data looks fine, the worker performance looks fine, and the task looks fine. Once that is done, then you actually have debug and test your human computation. And sampling, as it was mentioned in the previous talk, is super crucial here. Sampling from good people, from good content. Okay, so how can we do this? So we came up with this technique called HIDDINGS, which is Human Intelligence Task Data-Driven Inquiries, which is basically, we borrow the idea from CAPTCHA. So you have the control term, and then the actual term that you want people to enter because it's the label you want. So we're going to automatically generate questions from the data set. One is an algorithmic question, very easy to compute the answer, and the second is more of a semantic question. Those are mostly to see if the workers are alive, they're doing what they're supposed to do. And then go for the third question, which is the question that you really want the answer. So here's an example on a very difficult problem, which is tweet classification. I'm saying very difficult because when people talk about labeling social data, it's very, very hard. Believe it or not, it's very, very hard. So the tweet here is we want to know if we can derive some categories from a tweet. Very, very simple, right? So we show a tweet, The branded, no account, just 140 characters. And we have two questions. Those are the hidden questions. The first one is, how many hashtag words, so words that begin with hash, are in the tweet? So no hashtags, 1, 2, 3, or more. So you can compute the answer already. So when you upload the data, you know what's the answer for the first question. And it's just a kind of a sanity check to the workers. The second is more of a semantic question. Does the tweet name any specific person? In this case, it's Paul Allen, so the answer is yes. So you can use a name entity extractor to see if this is correct. And the third question is the question that you really want the answers. And you want to know if the tweet is worthless, trivial, funny, makes me curious, contains useful information, or is important news. And as you can see, I'm using these soft labels. So I'm not using yes, no, I'm not using a Likert scale, because those things don't work. You have to find labels that actually work for people. And we spend a lot of time working on these questions, because the question number 3 was the problematic question. Question 1 or 2 were working very well, but we started using yes, no, we used a Likert scale, and we couldn't get the labels that humans were able to work better until we found this labeling. Another example is to use micro breaks. So basically, diversions as part of the task. So you do some task, and once in a while you have diversions. And this is work done at Google, and they show that it's very, very useful and can improve the work quality, even if you, in the case that you have micro breaks that are part of the context, that are even better. I'm going to touch something that is also a part of debugging, but it's the other way around. I was talking how to debug tasks that are part of humans and machines. You can also do what we call human debugging. So we're going to use humans to debug the ML model that you just built. So we call that beat the machine. So you're going to find cases where the machine is wrong. In particular, what is called the unknowns. Things that the model believes that it's not doing a lot of errors, but actually the model is wrong. So not only you can use programming techniques to identify bugs, but you can also use humans to identify bugs in the modeling. And since I have 10 more minutes, I'm going to talk about algorithms for quality control. Quality control is an extremely important part of every human computation task. It's not just the workers are bad, but it's bidirectional. So you may think the workers are spammers, but the workers may think you're a very lousy requester because you don't know how to ask questions. When you assess work quality before the task is uploaded, during the task, after the task. Okay, always be assessing quality. So before that, you can run qualification tasks for screening selection of people. During, you can also have random checks to make sure that people are doing what they're supposed to do. And at the end, you just run the number of metrics, and you make sure that people have passed on the answers, same as a test. How do we measure work quality? We can compare against another person, another label, or you can build predictive models of the labels. And you can also try by yourself, or you can use tiers approach of different workers. Comparing to known answers, this is called kind of goal sets, honeypots. You have an answer, and I just want to make sure that I pass or not. The problem is you have to produce these goal sets. Are expensive. You have to have experts that are going to produce the goal sets. You have to maintain them, because people may have already guessed the goal sets. So next time they do the work, they're going to already know, or maybe they pass the answers to other workers. Comparing to other workers, that is called consensus, redundant label, or plurality. It's a well-known metric for measuring agreement. Again, in terms of cost benefit, it's redundancy. So you're adding stuff that you already know to do this. Qualification tests, I'm going to skip briefly. Advantages is very good, but disadvantages, it requires a lot of work for you to build a qualification test, and some people just don't like to ask a test before actually doing some work. Now, if you're going to go through for the algorithms used in practice, majority vote actually works very nicely. There's a school of thought that you have to use EM, expectation maximization, to do all this stuff. Get another label is another good algorithmic for getting the end results for the labels for all these workers. Vox Populi, very good for cleaning data. And then programmatic Go, this was done by the guys at Crowdflower. We at Microsoft have been working what we call adaptive algorithms. And the idea here is to use explore-exploit approaches where there's a kind of a quality-cost trade-off. And the idea is there are certain cases that you don't need a lot of workers, and there are certain cases that you need a lot of workers. So the point is, how many workers and when to stop. So if the query that I have to evaluate is Facebook and the website is facebook.com, maybe I need 1 worker. But if the query is solar storms and this is a website and I have no clue, maybe I need 5. So when to adapt, more or less. And the adaptation is going to be based on the complexity of the hit. Some of those tasks are going to be very complex, so I need more. Some of them are very easy, I need less. So the idea is to define stopping rules, which is basically algorithms that know when to stop this, asking more or less labels, and know when to stop if I have historical data for all these workers or if I don't have historical data. And if you can do this, you can build ground truth automatically. Full paper is going to appear in SIGIR in a couple of months. Now, there are some practical considerations here. So all the expectation maximization approaches, they're very good in theory, but in practice, you have to have historical data. And sometimes this is hard, and you're going to have this kind of cold start problem because you don't have historical data. Aggregation rules based on majority votes is actually a very nice alternative. You can do majority, you can use unanimity, and you can use quota. So majority, if you have 5 workers and I have 3 say yes, 2 say good, it's majority. But it's not enough. So maybe you want to use quota. So you want 70% of the workers to say yes, or 70% of the workers to say no. And finally, you can do something completely different, which is behavioral features. So the idea here is to fingerprint the task. So you're going to trace the worker using JavaScript to know where they put the mouse, where they click, when they stop, when they took less time, more time. And you can do that getting the metrics. This notion of fingerprint is going to tell you the fingerprint of the task. And then you can compare other workers to see if they're more or less in the same fingerprint or not. Fresh out of the oven, there's this paper by the Google guys on a system called Wernick. They're actually it's a very nice tool for annotating information extraction. They're using a weighted majority vote, all fingerprinting, and they show that you can do better than any of the EM-based approach if you just use behavioral data. So far, this is great, but looks like a ton of work. Programming is hard. Programming for machines is hard. Programming for machines and human is harder, so this should not be unexpected. Remember, we want good labels. Data quality and experimentation designs are preconditions to make sure we get the right stuff. All the labels will be used for ranking, models, evaluations, etc. Don't cut any corners. I show you the programming side. So how to code a hit. You can use patterns. You can modularize the same way you're going to chop your piece of code. You can do all these pipelines, little workflows. You have to test and debug. You have to maintain, and then you have to monitor the work performance. Last 2 slides. The first one is, if you're going to work on computations that involve machines and humans in synchronization, it's a very delicate balance, but there's a lot of potential. Now, the most important part for you guys as designers or architects or data scientists, you have to know when to use a machine or a human for computation. Labels for the machine, not be labels for the humans. The usual approach is I have these features that I want to build a classifier, and people just take that and make it a web form in Mechanical Turk to get the labels. Those are labels for the machines, may not be labels for the humans. Find those labels. Then debugging code executed by humans is hard, but you can do it. At the same time, why don't you just debug the machine model with humans? So it's a win-win. You're going to debug humans, but at the same time, the humans will help you debug your model. And the final bit is the best algorithms for the machine may not be the best choices for humans. Okay, so there's heavy data-driven algorithms that work very well, but sometimes might not work with humans. So takeaways, and I'm just done with this. Repeatable label quality at scale works, but requires a solid framework. Use all programming principles. Always use programming principles. If you can, data management. 3 aspects that actually really need your attention: workers, work, and task design. And you cannot do this by yourself. Okay? There's a lot of skills and expertise required: social, behavioral science, human factors, algorithms, economics, distributed systems, stats. That's my email, my Twitter handle. Thank you very much for the time.
Thank you. Gracias por la presentación. Omar Alonso. Since the talk was a little bit top-down, I'm going to sum it up for you. So you either memorize the whole talk if you want to acquire good labels, or the other option is hire a German psychologist. They do this stuff for a living. Okay, thank you very much. So for Q&A, try to keep your questions short because we are trying to set up everything for the next speaker. And I'll come to you with a microphone. Yes.
First of all, I would like to thank you for the talk. I've been working in the area of active learning, and all you said was very, very relevant to what I work on. And then the biggest question is, with given the number of people that work on social data, and as you pointed out, getting quality labels on social data is very, very tough. Why isn't there more focus on the kind of work that you talked about today? Like getting good quality labels. Why is there more focus on the type of machine learning models rather than the labels?
Thank you very much for the question. That would have been my question too.
Great question, and thanks for asking the question. I think the answer is everybody wants to work on the modeling, which is kind of the sexy part, features, you roll these metrics, great stuff. But as we acquire more data, and we're starting to find out that humans annotation, all the labeling is getting more and more important. Facebook example is one of them, okay? So even they leak the editorial guidelines, you can read them, it's around 30 pages, and people are questioning that if you don't get the right labels, the algorithms are not going to work perfect, as Ricardo mentioned before, right? So you're going to have all these biases, and you have to correct. And in a lot of cases, you need humans in the loop. This is going to get worse. It's not going to get easier. It's going to get worse. Why? Because we have Facebook, Twitter data. Who knows what we're going to have next week and next year? And those things guess what? They're going to get even harder because everybody uses the same thing. Give me data, features, labeling, optimization, and prediction. And everybody knows how to move from features upwards. On the data, well, someone will do it. But you have to own it. If you don't own it, you won't get good quality, in my opinion. So this is, I think, it's just getting started.
Thank you very much. If you want to tweet about this awesome...